To build a violin, you start with the heavy removal of raw timber, transitioning to the exact opposite, peeling away tissue-thin, translucent layers of spruce. This acoustic blueprint for the standard four-string violin was established by Andrea Amati in the 1560s. For nearly 5 centuries, those proportions have remained largely untouched. The reason this process has never been handed over to machines comes down to the material. Wood is a highly inconsistent organic medium. No two pieces of timber share the exact same density or stiffness. Because the material varies from tree to tree, a rigid blueprint or a set of automated measurements will fail. A machine programmed to cut to a precise millimeter might hit a dense pocket of grain and fail to account for the wood's natural resistance. Creating an acoustic masterpiece requires a responsive conversation between the luthier and the material. The maker must continuously listen and adapt their carving to the unique physical traits of the raw wood in front of them. The conversation starts with the selection of tone woods. For the front soundboard, makers choose spruce. Spruce has a very low density, which allows it to vibrate easily and transmit high-frequency sound waves. The back and sides of the body require the opposite approach. Here, luthiers use maple, a high-density wood that acts as a structural boundary to reflect that acoustic energy outward. This maple is often selected for a visual phenomenon known as chatoyancy. Chatoyancy is an optical effect where the flamed bands of wood grain appear to shift and move, depending on the angle of incoming light. To protect these wooden boundaries, the luthier carves a 1.2 millimeter groove around the outer edge. This is the purfling channel, a tiny trench that holds a structural wood inlay called purfling, which prevents the edges of the instrument from cracking. Where these purfling strips meet in the corners of the instrument, they converge into a sharp, perfectly mitered point known as the bee sting. These exterior woods and decorative inlays establish the physical boundaries of the instrument, but the luthier only achieves true resonance by thinning the plates from the inside. This internal carving is done through graduation. Graduation is the precise mapping and scraping away of the interior thickness of the wood plates to achieve a specific flexibility. To measure their progress, luthiers suspend unattached plates in the air and tap them, listening closely to the wood's resonant frequencies. A thick plate produces a scattered thud, but as it's thinned, the muddy feedback organizes into a clear pitch. The target is thinning the wood until these frequencies perfectly align into 2 distinct geometric patterns, Mode 2 and Mode 5. Because the spruce and maple are naturally unpredictable, this auditory feedback loop is the only reliable way a luthier can achieve mathematical acoustic results within an imperfect organic medium. Once the plates are joined, the instrument must be chemically sealed, a process that begins by melting solid golden colophony granules at 350 degrees Fahrenheit. Colophony is a highly refined pine resin used to give the finish its hardness and luster. Following historical formulations, this molten colophony is carefully combined with linseed oil and beeswax. When applied to the wood and exposed to air, this mixture oxidizes to form a new compound called linoxin. Linoxin is the durable, cured state of linseed oil. As seen on these drying violins, this cured linoxin layer acts as a vault. It permanently seals the wood from environmental moisture while maintaining enough physical flexibility to preserve the instrument's acoustic freedom. The varnish acts as a vital protective skin, permanently locking in the tuned frequencies established during graduation. The final step of the process takes place in the hidden interior of the finished body, accessed through the tiny end pinhole. Here, the luthier inserts the sound post. It is a small, unglued spruce cylinder, delicately maneuvered into place, widely considered the soul of the instrument. In this 3D cross-section, a critical rule of physics is revealed. The sound post's wood grain must sit at exactly 90 degrees relative to the top plate. This perpendicular alignment creates an efficient bridge, transferring acoustic energy directly to the backplate. Because the pillar relies entirely on friction rather than glue, repositioning it even a millimeter can cause a sudden drop in clarity or a loss of warmth in the instrument's lower register. From navigating the inconsistencies of raw timbre and tuning invisible frequencies, to executing chemistry and balancing the tension of a single hidden pillar, the violin remains one of the few objects that refuses to be perfected by a machine. It has survived 5 centuries exactly as it is, because its voice still requires the human capacity to listen.